Embed has never been so exciting. It's life-saving. It's life-changing. It's dream-making. And it all starts with this chip. A small and mighty computer the size of a credit card, with embedded chips and processors, enabling our passion and curiosity to solve anticipation of a problem, mitigate risks, and create solutions that improve business and life. The potential that lies behind executing dreams is so tremendous. If we fail to realize them, the responsibility lies solely on us. So dream away. Be great. Enclustra. Embed with us.
Thank you all for coming today and for sticking around. I know you've consumed an awful lot of information today, and so these last two presentations should go fairly quickly, and they're a little bit lighter and not as much technical intent or intensity. So let's see. So, yep, as I said, most of the program today was sort of, deep tech talk. And what I thought was it would be a good idea to sort of just present a simple use case for Enclustra modules and how we've gone about using them in the past and how you might too. So, I run a design company called LSF Design. We're just outside of Boston. We've been in business since 2008. We primarily do embedded design services. Lately, we've been doing more and more Enclustra work. In fact, I'd say, I work with Enclustra products and Enclustra Corporation every day. Like Tristan had said, we work a whole range of industrial applications. Back in 2015, I got a phone call from a small FPGA SoM company in Switzerland that honestly I'd never heard of. But they had asked if I would be interested in representing them here in the United States. And as it so happened, the founder of the company was going to be at a trade show in Boston a couple weeks later. So I went in and I met with him, and we sort of agreed on what kind of work we could do for them. And so we've been working with Enclustra since 2015, providing sales support, technical support, a range of other shows like this, trade shows, as well as distribution services for companies in the U.S. that are unable to buy from foreign vendors. I mentioned that we primarily work on embedded systems. And when I say embedded system, I say in a general sense, a system that has four major blocks, right? The first is a processing system that's made with DRAM, Ethernet PHYs, user I/O, stuff like that. The second block is sort of typically a programmable piece, either an FPGA, standalone FPGA that's working with a processor, or an SoC type situation where the FPGA is part of the IC. And the programmable piece is where you guys can first start implementing what you need to do for your custom application. Beyond the programmable logic is typically some sort of sensor, right? It's either a sensor that's detecting something, whether it's inertial movement or whether it's sound waves or whether it's RF or anything like that, or if it's maybe sort of outputting something, if it's driving a sound or driving some sort of other mechanical interaction. Further upstream, and so the sensors is obviously the biggest place where you guys could, implement your particular design features. Upstream of the processor is typically a host computer that's either consuming data and displaying the results of it, or analyzing it, or somehow storing it, or whatever the application is. But the host is obviously the biggest place where your design is going to be manifested. And of all those four places, the processing system with the DRAM and the Ethernets and the user I/O is sort of the piece that you don't have to worry about, right? That's what the SoM is doing now. And as Roland has said, and some of the other messaging today, the SoM is sort of quickly becoming the component that you guys design into your custom design, so that you can worry about all the stuff that you do best, right? This is done technology. There's no reason to redo it. So, my first job out of college was at a company called the Massachusetts Computer Company, or MassComp. And at MassComp, we were designing it's kind of a niche computer, but it had a strong digital back end and an analog front end. And scientists loved to use it because they could hook up their experiments and everything was done for them. They could capture data and store it. The computer was based around the 68K processor. And if you're familiar with the 68K, it's just a processor, right? There's no, there were peripheral chips you could buy for it. But, at MassComp, we had to design the Ethernet interface. We had to design the graphics card. We had to design the memory system. We had to design everything, the second level caching. But, you guys don't have to do that anymore. The SoM does that for you. And just to sort of bring home that point, that's why Enclustra is selling these SoMs, is to make your life easier and to make it easier for you to implement your applications. So what are the benefits? The biggest, of course, is a reduced development time. We figure it's 12 to 18 months saved man months saved in engineering time and cost by implementing a SoM. Reliability is improved greatly because Enclustra builds these SoMs, they test them, they run them through environment chambers. They've been life cycled, and the bomb is bulletproof, and they're taking care of all that. Scalability, as Roland mentioned, within any family of Enclustra products, you can scale up and down. You can design your baseboard for the smallest device, and if you realize that that's too small for your application, you can certainly upgrade to the next size SoM. And the same, you can scale up and down. You can have products with different price points. And cost effective, sort of all the above makes these things cost effective. So a few years ago, we were approached by a customer that was looking to implement a Sonar transmitter. It was a relatively simple concept, but they had a very strong engineering department, but their engineers were sort of geared towards their specialty, which in this case was the transponder design and the power amplifier designs. So they asked us if we could help with the FPGA code, develop the processing system, get Linux booted for them, and develop an application that ran on top of Linux and interfaced with their host. They had already chosen the SoM, the SA1, which is the Cyclone 5 part. For any of you Intel fans out there, Cyclone 5 is a relatively low-cost FPGA or SoC, and Enclustra has a sort of great SoM for that. So they had a certain set of design requirements, and what we were able to do was take an Enclustra PE1 baseboard and the SA1 SoM, and couple it with an Analog Devices DAC demo board, and sort of immediately get waveform generators running for them within, say, like a 2-week time period, to prove to them that this could be done and it would work well with the DAC that they wanted to use and the SoM. And all, while we were continuing to develop the FPGA for them, they were doing their board design and getting that done, built and fabbed. So Sonar, I think we all know Sonar to some level, right? It's sound navigation and ranging. It's basically used for seeing underwater, right? There's two main types of sonars. There's a passive sonar, which is really nothing more than a microphone that's dropped below a boat in the water or from a buoy. And there's active sonar, which sends out a wave of pulses and waits for the echo return and sort of can figure out where something is underwater. Commercial fishing boats in particular use sonar quite a bit. They use what they call multi-beam sonar, where one of the sonars is sort of working in a horizontal plane and the other is working in a vertical plane. So they're able to both see the ocean floor. They can see targets that they're looking for, in this case, fish. They can also see the depth that the fish are at. So they can set their nets and then go catch the fish. Of course, the biggest application that we see more than anything else is in the movies, submarines, Navy, and they use all types of sonar, of course. Sonar is divided into 3 basic frequency ranges. There's a low, a mid, and high. This sonar transmitter that we're working on was considered a high frequency sonar. We're transmitting anywhere from 10 kilohertz to 100 kilohertz. So a typical sonar system includes a transmitter and a receiver for an active sonar, as I mentioned. A host system upstream will sort of send the commands down to a unit that's somewhere in the boat. That unit will transmit the waveform information out to the transducers. Then they will switch to listening mode and listen for the echoes coming back through a receiver, which may have some DSP or other sort of processing in it. So this is kind of a textbook diagram of a phased array transmit system. There's 3 ways in the sonar to direct the beam when you're doing beamforming. The first is by delaying different channels. The second is by changing the amplitude of different channels. And the third is by changing the shape of the wave. In this design, we needed to have an arbitrary waveform generator that could be loaded by the host on command and then sent out with the delays and whatnot to the phased array. So in this design, there were 5 modules in the sonar housing. Each module had 8 transmitters on it. The transmitters worked at a very high voltage. They're anywhere from 100 to 140 volts, sending out to the transducers. Each transmitter board had a single SoM on it. Those SoMs all talked through a switch back to the host computer. You can notice one of the SoMs, one of the modules in this diagram is called the master, and that's how we kept timing for all modules together, was by having a synchronizer that went between daisy chain on the back lane to the other modules. So this is a little stack up of the system we had, with the operating system on top. It was a standard Linux OS from Intel. Running an application software that we wrote at LSF Design, and then the FPGA logic that we also designed at LSF. All that is running on the SoM. The D to A converters, the amplifiers were on the customer's transmit board, and then of course the transducers were further out in the bell, the housing. And the design, the FPGA has a number of control and status registers that the user, the host, could set up to define the waveform. We'll get into that in a minute. So, it's a little block diagram. It's kind of simplified. The blue blocks are Intel IP. The rest is the blocks that we developed at LSF Design. Control status register, of course, is where the waveform gets described. The wave processing block is where the waveform itself is generated. That waveform is sent out to all channels simultaneously. The channel delays are implemented in the channel blocks, and that goes out to the DACs and then out to the transducers. So it's just a quick description of the waveform generator. The wavetable itself held sort of one cycle of the wave. It was 360 degrees of a waveform. By default, it was a sine wave, but the host would load sort of any shape that it needed to send out. Again, the registers defined everything about the ping that was to be sent out, including the number of cycles to transmit, the frequency, the gap between bursts, and any other sort of details, including the delay, which is in the channel block there, that's in gray. So there's a picture of the board. You can see the SoM at the bottom, along with the Ethernet connector. That whole bottom portion is the whole of the digital world in this design. Everything above that are the high voltage amplifiers. The cables go out to, they, sort of kindly did not make me test with transducers in my house. So I had some load resistors that were able to sort of absorb the load, and I was still able to see the voltages as if they were on the transducers themselves. I did get to hear it in the tank. They had this customer in particular had a large sort of very large swimming pool in the back of their office space where they would put the transducer, where they put the whole sonar and fire it off, and it was pretty loud. So the Enclustra build environment. Enclustra provides this ecosystem for all their users that, as far as I can tell, is unparalleled in the industry. You're able to download the schematic of the module, a sort of step files for all the modules, sheets with all the delay information for all the critical traces on the module, reference designs, and a build environment for Linux. But the point is that they're able to sort of anticipate exactly what you're going to need to know if you lay out a backplane. At LSF, we have done, more than a dozen backplane designs, and being able to know what the trace length is on any given signal that's coming off the connector has been invaluable to the PCB layout folks. So we can, you're not guessing, you don't know what the delays are, but you can figure it all out. And so the build environment for Linux, it works with all the modules, whether it's the Xilinx part or an Intel part or microchip. You download it. It works much like a Yocto environment. It's a menued kind of system. For Enclustra, you go in, you tell it what module you want to use, what baseboard you're using it with. Whether it's typically, obviously, it has to be an Enclustra baseboard, but whatever is most similar to yours. And it downloads everything it needs to build Linux for you. It builds U-boot, it builds the file system, and it builds the kernel. And you're really just ready to go. You can then go into any of those three, sort of subdirectories and customize them any way you want. If you're, prone to be customizing Linux stuff, that's how you do it. And it's really pretty bulletproof. It's great. This is just a sort of a screenshot for the build environment. So when we first started testing and showing the customer what we had running on our bench, they sort of asked, what are you running? What's this application that you're running? And we told them that was a sort of an in-house diagnostic that we had, much like probably most of you have at your business. And it was just a tool that we used to peek and poke registers, to dump sort of memory, to sort of make little sort of test routines and whatnot. In a lot of ways, it's not too dissimilar from the FPGA manager that Enclustra sells, but it's highly customizable. It's just in C, and it works pretty well. So they asked us if we could sort of extend it to work with their NI test bench stuff that they were running on the host. And so we did that, and we added sort of a couple of different threads, one that was just listening for commands coming from the host. The other was sort of sending health data back, telemetry data for voltage and current. The thing about sonars is that once they're in the water, you can't tell if a particular transducer is working or not, unless you sort of can see the voltage and current loads that are going on for every transducer. So that data was critical for them, and it was running all the time. And they were quite happy with it, and we were able to sort of get it all running very quickly for them. Just another quick screenshot. So, in summary, using this whole ecosystem provided by Enclustra was sort of invaluable to us. We're able to pull all these different pieces together very quickly. The customer was extremely happy, and we were able to do it in a sort of both a timely and a cost-effective manner. And if it wasn't for sort of everything that Enclustra helps with, we probably wouldn't have been able to do it. So it's great. I highly recommend it. And if you need any help, let us know. Thanks.
Embed has never been so exciting. It's life-saving. It's life-changing. It's dream-making. And it all starts with this chip. A small and mighty computer the size of a credit card, with embedded chips and processors, enabling our passion and curiosity to solve anticipation of a problem, mitigate risks, and create solutions that improve business and life. The potential that lies behind executing dreams is so tremendous. If we fail to realize them, the responsibility lies solely on us. So dream away. Be great. Enclustra. Embed with us.